Okay, so I think we're now live for our last Google Hangout. I forgot to mention something in class, but I wouldn't mind doing something else, some other sort of review if you guys want it between now and the actual exam itself. We could talk about that maybe on Wednesday if there's time. I know that some people go to Origins to study, and I don't know if that's something you guys are. If you guys go, like if you all were to go to Origins on a Sunday night, I'd be happy to go over there and meet you guys and help you out for a little while, something along those lines. So, just something to keep in mind. I wanted to make sure I had a periodic table online that I could pull up. All right, good. I'm kind of hoping you guys will come on here and ask some questions. I did create that sort of outline specific to the final exam. I know it got a little bit long. Let's see, where is it? Here it is. Let me pull that up real quick and I'll show it to you guys. Okay. So, and I'll make it bigger too. I think that'll make it a little bit easier to read. Okay, so it's about, well, it says it's 2 pages long of different things that you should be familiar with. Why don't I, while we're waiting for people to show up and ask questions, I don't know if somebody may ask questions, may open up the Q&A app. I haven't opened that up yet. Hey, there is already something there. Emma. I'm just working, let's select it. Can you review ice charts, please? I want to make sure I have them down. Absolutely. Let's look at the ice tables. So I think I have. Okay. And so the thing is, there's a couple different ways to do this with ice tables because it depends upon what you're looking for. So ice tables, okay. Ice tables, okay. And the ice stands for the initial conditions. The C stands for the change. And then the E stands for at equilibrium. Okay. And so when going over this, usually you have some sort of a reaction. And let's just use a real basic one to start off with. N2 plus H2 is in equilibrium with NH3. And it has to be balanced. So you have a 3 here and a 2 there. And you have your ice table. And so a lot of times they'll say, oh, you have, and let's say these were all gases. And gases have that funny feature of you could actually do this using Kc or Kp. So Kp means you're doing it in atmospheres. And if you're doing Kc, it means you're doing concentration. So those are interchangeable, basically, in the table. I will say this, though, the relationship between Kc and Kp is different. Now, you no longer have to do that on the test, so you don't have to worry about that, but just know that you can use atmospheres and you can use concentration using the form molarity. You could also do it with moles. So something to consider. So let's say you were doing this and they said, okay, you start with 2.5 atmospheres of N2 and 3.5 atmospheres of H2 and then 0 there, what will it be at equilibrium? And usually they have to give you some sort of a Kp. So Kp is equal to 3.5. And this is totally random. I'm just making these things up. So what you end up with is the change. And so you're adding some change over here. Well, there's 2 of whatever you're adding. So you're adding 2x. okay? Whatever you're losing over here, you're losing X because you are losing from the side that has some already, and you're gaining on the side that doesn't have any. And you're losing 3X because the coefficient is 3 right there. So you end up with, at equilibrium, you have 2.5 minus X. You have 3.5 minus 3X, and you have 2X. And then you have a situation in which you have the products over reactants. So Kp is equal to NH3, and of course that's squared because that's the coefficient, divided by N2 times H2, and that's cubed. So what you end up with is 3.5 is equal to the NH3, which was, so you have 2x squared over N2, which is 2.5. And the H2, oops, sorry, I forgot the whole minus x thing, huh? So very good. Okay, minus x, and that is squared times 3.5 minus 3x cubed. Now, I'm going to tell you this. This is an absolutely ridiculous example because there's no way mathematically I'm going to make you do something like that. They're not going to make you do something like that on the test. That one's huge to solve for x. Whatever they do is going to be a little bit easier to solve for, but it kind of gets you going in the right direction. So sometimes they give you all the numbers and you have to solve for k. Sometimes you're solving for x, so that's the change, whatever the change is. Maybe they're asking you to solve for the equilibrium concentration of the NH3. But that's basically the setup. If they gave you, let me give you another example. Let's say you're doing an ice table, but you're doing it with solubility. So now you're doing it with the KSP. And so you have AgCl, which is a solid, and it's kind of in equilibrium. It's going to Ag plus, which is aqueous, plus Cl minus, which is aqueous. Cl minus, which is aqueous. Okay, and you remember that solids and pure liquids cannot be in the equilibrium equation. So for this, they're going to give you a KSP being equal to something pretty small. Let's say that it's 5.0 times 10 to the negative 10th. And so if you're going to set up an ice table, and the Ag for the solid, it doesn't matter because it's totally not a part of this situation. And so you start off with, let's just say you start off with 0 and 0, you're dropping it in there and you want to see what the solubility, the molar solubility would be. Well, you're adding an S to each one. And so at equilibrium, it's S. And so your KSP is equal to the concentration of the Ag plus times the concentration of the Cl minus. So KSP, oops, sorry, we already have that one. I'm going to start using the numbers and stuff. You would end up with like 5.0 times 10 to the negative 10th is equal to S times S. So basically it's S squared is equal to 5.0 times 10 to the negative 10th. And you would end up square rooting both sides. And S, which is the molar solubility, is equal to the square root of 5 times, and when you square root an exponent, it just divides it in half, times 10 to the negative 5th. So it's something like 2 something times 10 to the negative 5th. And that would be the molar solubility of, you could say AgL, Ag plus, or Cl minus, since they're both S. So that was a simpler version of it, but hopefully that helps you a little bit in identifying how to solve those ice tables. You can use them for, so ice tables can be used for, they can be used for anything really. You don't often use them for KSP because you can see how easy it is. But usually it's when you're trying to find an equilibrium concentration, or you are trying to find maybe you're trying to find K if they give it to you. The ones that you don't end up using it for are a lot of times with the Ka and Kb. Those ones, because those are acids and bases, they're usually not using ice tables for those. Usually they're giving those values to you, and you're using your calculations to find H plus or OH minus, something along those lines. It's so usually not those ones, but you know, Kc, Kq, Kp, Ksp, all of those I can see the possibility of using an ice table for. Okay, so hopefully that answers your question. Works out pretty well. All right. The next question I see on my list is, Mary Flick, could you please review hybridization and atomic orbitals? And we can do that. Okay. So hybridization actually is a very simple concept, and the way that they look at it is probably a little bit, it makes it sound more difficult than it is. So let's start off with the basics of it. When we're talking about hybridization, you're talking about sigma bonds, sigma, which are single bonds, and pi, which are your double, triple bonds. Okay. So if we have, let's say we have H2, so it has H, okay? And let's say we're comparing that with O2, which is O double bond O. And let's say we're comparing that to N2, which is N triple bond N, okay? So I'm gonna switch the color a little bit. And so right here, this is a sigma bond. That little symbol means sigma, okay? And then for doing this, for the double bond, the first one is a sigma, and that one is a pi. Okay, if we're doing a triple bond, this one's a sigma, that's a pi, and that's a pi. So there's two pi bonds. 2 pi bonds. Okay, so sigma bond is just whatever the first bond is, and a pi bond is anything on top of that. Now, to keep going with that idea, and it's all going to come back around, is that you also have S and P bonds. Okay, and the S is for the S orbitals, and the P is for the P orbitals. So if you're looking at carbon, okay, H, 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 okay? And so it has 4 bonds around the outside. You have carbon, which has a 2s, it has 1 arrow up, 1 arrow down. And then in its 2p, it has 1 arrow up, 1 arrow up, okay? So it has those 4. I should label this as 2p, okay? And so what we've already covered, actually, and I didn't include, is the 1s. So it has 6 valence electrons, but really the ones in the 2 in the second level, those are the ones that are going to be used for hybridization, okay? So I'm going to go ahead and circle these bad boys, because what's going to end up happening is, and I'm going a little bit more in depth than you need, because people keep asking this question, and I thought I've answered it. So I'm not sure what's happening, why people aren't, maybe they're wanting more information. Okay. So what happened is, this is carbon, okay? And now there are 4 hydrogens. For H, you have a single bond. You have a single bond. You have a single bond, or not a single, but a single electron. So what's happening is, basically, each one of these is moving up into this, right? And they're becoming paired up. The 4 H's are combining with the 4 electrons because what was once here has moved over there, if you'll notice, right? This one right here moved over here. So what happened is that you combined an S with each of these p orbitals, and so you have what's called an sp orbital. So each one of these, and these are all S's right here, okay? And so it's a small, like I wish I was a better artist. You know what I should do? Actually, well, okay, let me just start off with this. So basically what you end up with, I'll show you that picture in a second. When they're asking for the hybridization, they're asking for the hybridization on the central atom. So there are a total of, basically the easiest way to do it is this is S, P, P, P. So it's sp3. That's what you have on that central atom. There's sp3. Okay. If I had C, double bond C, H, 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 you'd say, okay, this carbon right here, there's 1, 2, 3. So S, P, P. And you don't count both bonds there, it's just a bond. So it's sp2. sp2. Okay. So let me see if I can, it'd be really cool to show you guys the hybridization. sp3 hybridization. If I can find an image of this. So what ends up happening is, there we go. Let's use this picture. Oh no, don't do that. Okay, there we go. That's pretty funny. I think it's Arabic on the top part of it, which for those of you that speak Arabic, you're in luck. All right, so you look at that, and what you have is these are sp3. There's this sp3 right here. What happened is an S combined with the 3 p orbitals, and you can see there's an unusual shape for all 3 of those. So here's this right here. This is a CH3 or CH4. Sorry, CH4, not CH3. And so that's basically what happened. Now you don't need to know any of this. You don't need to know any of this at all. You only need to know what I told you, which is that around the central atom, however many things are bonded on that atom, that's the hybridization. And that's sigma and pi bonds using the S and P orbitals. That's all. So those are the atomic orbitals. So, and you can fill those out, right? Same as the electron configuration, and that's what's used for the hybridization. So I believe that's answered all the questions. I've heard several people ask, like, what is hybridization? So that's what hybridization is. You don't need to know that part of hybridization, but if you can do this hybridization, then you're just identifying the bond type. If one of you would actually ask a specific question, because I have no idea what this is in relationship to. I keep asking for specifics and people just keep telling me hybridization. So that's all I've got. But if several people are asking, it must be a question. So if you guys could somehow get me the question number or whatever, then maybe I could address it in that way. Excuse me, I feel like I'm drying out already. All right, so I'm going to consider that one done for right now. And Aria asked about sigma and pi bonds, and I just covered that. So I'm going to say done on that one too. Okay, Ephraim, how do you know if a substance is amphoteric? Let's do that one. Okay, amphoteric. So there is two different. Oops. Sorry, I meant to share the bamboo paper. Okay, 2 different types of phrases that you have to deal with. And one of them is amphoteric, and one is amphiprotic. Okay, and really, they're almost the same thing. Amphoteric means behaves as acid and base. And amphiprotic means gives up and gains an H plus. So I would have to say that probably one of the easiest ways to look at this would be talking about something like HCO3 minus, okay? So can this give up? Can it give up an H plus? Yes, it can give up an H plus and become CO3 2 minus. Can this gain an H plus? So if we added an H plus here, plus H plus here, yes, we get H2CO3. So if you give up an H plus, right, that is a, if you're donating it to something else, right, that's a Bronsted-Lowry acid, okay? If you gain an H plus, that's a Bronsted-Lowry base. You're a proton acceptor. So in this case, you are both amphiprotic and amphoteric, and I think that's why it's used so frequently. It's almost interchangeably. They have different definitions, and I'm sure that there are examples out there where something can behave as an acid or a base, and it's not amphiprotic, I guess, but most often, at least in AP Chem, it is. Water is another perfect example. So we have water plus HCl, and you end up with Cl minus plus H3O plus. And in this case, it's a base because it accepted an H plus, okay? And it acted as a base. Now, it accepted a proton, so it's amphiprotic too. So here, H2O plus, we'll say NaOH is going to give us actually, you know what I'd rather do? My favorite example in this case, I don't know why I didn't think of it right away, is NH3. And you come up with NH4 plus OH minus. And now it acted as an acid because it was a proton donor, giving the H right here, okay? So again, behaves an acid as a base. And that's how you know if it's amphoteric. If you can make it be an acid and you can make it be a base, then it's amphoteric. You could, and I like to think of it just as amphiprotic, meaning that it has an H that it can give up and it has room to gain an H. That's how you know. Now, most frequently, water being the exception, it has no charging, but most frequently, it's an ion. And you can see it, especially if it's already negative. So you've got HSO4 minus or HSO3 minese, you know, it's already got one to give up. H2PO4 minus, HPO4 2 minus, right? These are all amphoteric or amphiprotic. They also, with the exception of HSO4 minus, happen to be weak acids. You don't often see it with bases going both ways, but you can see it with the acids or weak acids. So hopefully that explains if you know it's amphoteric or amphiprotic. All right, done with that one. Now, Aria, before you do gravimetric analysis, I think I want to do F-frames because it's continuing the acid-base stuff. So we're going to select that one right now. And how do you find conjugate acid bases? Are conjugates usually strong or weak? Okay, so I did this, I think I did or I hope I did a video for it. I thought I did a video for it. So you can watch the video, but just no time like the present to review. Conjugates. Anytime you're going to have a conjugate, it's only with weak things, okay? So you could say it's the conjugate, but it doesn't make as much sense, right? If I have HCl and it dissociates into H plus Cl minus, you could say, oh, look, Cl minus is the conjugate of HCl. Well, that doesn't really make a lot of sense. Cl minus has no pH. It doesn't affect pH whatsoever. It's just there. So we probably wouldn't do that one. However, you would do that for NH3, okay? So NH3 plus H2O, I just did this one, but let's do it again. NH4 plus OH minus. So NH3 is a weak base, and this is its conjugate acid, okay? I should probably do these in different colors. it'll make more sense. It'll be easier to identify as we go through this. So, all right. So this is your weak base, and this is its conjugate acid. And then right here, you could say, well, this then is the weak acid, and here's its conjugate base. Okay. But really, the one that we're focused on is more this one right here. Okay, because that's the weak base, and here's its conjugate acid. All right. So let's pick another one. Another favorite of mine, HC2H3O2 plus H2O gives us C2H3O2 minus plus H3O plus, okay? And in this situation, since we already started with orange, we'll leave it there. This is your weak acid. This is its conjugate base, okay? And then this is then therefore weak base and its conjugate acid. And really, here, you're looking at this one, okay? Now, the reason I say that is because these are stronger than water would be. So when you look at these, that's how you're gonna know. And when you look at this, whatever the weak is, this without the charge on it, that's the stronger version. So here's a weak acid and a conjugate base. How strong is that conjugate base? It's not nearly as strong as the weak acid is. Okay, but it is still strong. If you throw some water in there, it's gonna pull an H onto it, boom. And really, because these are all equilibrium, that's the other thing. These are all in equilibrium, all right? It would much rather, in fact, I should make a big arrow. It would much rather be on this side than it would prefer to go the other direction, okay? That's why the K's are so small, right? So if I say the K is products over reactants, well, products, the concentration of the products are so much smaller than the concentration of the reactants. Ergo, K is so much less than 1. Okay, so it wants to go back that direction. So they're always weak. They're always weak, but a conjugate is, you start with a weak acid or weak base, and the conjugate's actually weaker than its original version, but it's still, and that's the whole point, is it's pulling H's onto it because it wants to go back to its molecular form. It would much rather prefer to be in its molecular form. Excuse me. All right, so let me see if I can, some other common ones that you might see, the CH3NH2 plus H. A lot of times they're combined with other things, but if I just do this real quick, because then it goes into buffers actually, conjugates go into buffers. And again, more going this way, but you'll end up with CH3NH3 plus OH minus. You could also say, hey, it produces OH minus, that means it's a base. So here is your conjugate, or I'm sorry, not conjugate, weak. This is your weak base. This is your conjugate acid. These are the ones we're really paying attention to. Another weak acid. Oh, I don't know why I didn't think about this before. HF. It's like a moderately weak, moderately strong. I don't know what you want to call it. Much bigger going in the direction, right? You get F minus plus H3O plus. So here is your weak acid and your conjugate base. Okay, love that one. Love it. So hopefully that helps you a little bit, get you going in the right direction. That should answer your question there, Ephraim. All right, now the basics of gravimetric analysis. Now this is one where I should almost do a whole, I don't know if I have, I don't know if I've done a video on this one. I don't know, I can't remember if it's on my list right now. I'm sure I have that list somewhere. It's gonna go to a new page. And gravimetric analysis. Don't worry about the big word. Basically, it's all about gravity separating out the, excuse me, I'm sorry, gravity separating out your, I can't complete a sentence, separating solutes, let's just say that, because that's what's dissolved in your solution. So you have to know about solubility, right? And for solubility, you have to know that all alkali metals, so that's Na+, K+, etc., nitrates, and ammonium NH4+. So these are all soluble. Those are the ones you have to have memorized. They're going to expect you to have memorized that, okay? So when you go in there and if you're writing like a net ionic equation, so let's say, for example, oh, you're going to form a precipitate, and it's going to be, you've got barium nitrate plus, let's say, sodium sulfate, okay? And you're going to form a precipitate from that. All right, and this harkens back to a little the way they used to do it. You had to predict the products, but come on, you've got to be able to figure this one out, right? So if you know all the sodium, and this is a double replacement. Oh, they just switch partners, so you end up with barium sulfate plus sodium nitrate, and if you remember that all alkali metals and all nitrates are soluble, what that means is that the barium is a 2+, as you can see, plus nitrate, which is a 1-, there's 2 of those, plus sodium, which is a 1+, there's 2 of those, plus the SO4, which is a 2-, and that's going to yield barium sulfate. I told you there has to be a precipitate. Well, that's going to be your precipitate, because what's the other one? It's sodium nitrate. It's soluble. That means it comes apart. It dissociates. And really, there should be 2 of those if you're going to balance it out. Okay. So now, if they're the same on both sides, they're what are called spectator ions. This is all part of gravimetric analysis, by the way, guys. So that means that the nitrates are both ions. They're the same on both sides. Those go away. The sodiums are the same on both sides. Those go away. So that just leaves you with barium plus sulfate, gives you barium sulfate. So if I write the net ionic equation, which NIE is often represented like that, you get barium 2+ plus sulfate 2-, and by the way, you should know that these are aqueous because they're ions in water. And it's in some sort of equilibrium with barium sulfate, which is a solid because it precipitated, okay? So great, we just know we had a precipitation. We put this, now we want to separate it out. How can we separate it out? How can we analyze the solutes we have? So one of the biggest ways to do that is actually vacuum filtration. And we don't do this one because we actually don't have the setup for it. We usually just let it go through a filter paper. The vacuum filtration adds a bit to it. But let's say we have no vacuum. So then what you would have is a filter. You would have a funnel. And then we put some filter paper in here. And so there's filter paper in there. And you were letting the solution that you've rinsed it with water, so then the water drips down, leaving you with whatever the solution is in here. So maybe, you get it in there. It's just okay. And we have a beaker. And this is dripping down. You have, because you're getting rid of all the water, and you're going to end up mass the filtrate. Oops. If I spelt it right, it would make sense. Mass the filtrate. Okay. So this is what's left over. This is what you dry out. And you're using gravimetric analysis. Again, you're trying to identify how much you have. You probably have the molarity of let me go back for a second. You probably have the molarity of the barium nitrate, and you have the molarity of the sodium sulfate, and you know how much the volume you added of each. And when you combine them, since you had moles of one and moles of the other, then you know how much barium sulfate you can produce at the end. It's probably not exactly equal. You'll probably have excess of something. So you should be able to know on the molecular level. This was one of the labs we did. You know, if you had to draw that, you know that you're going to end up with, let's say you have, you know, these squares and triangles, and the triangle is equal to the barium 2+, and the square is equal to the SO4 2-. So when they combine, you get that. And the maybe you have a circle represents the Na+ and it's floating on around, and maybe there's a rectangle like this, not a square, and that's the SO. Oh no, haha, it's not the SO4 2-. Don't let them tell you that. It's the NO3-, you know, and that's what comes out in the bottom. And maybe you have a little bit of extra Ba2+ or something like that floating around. Anyway, so that's if you have no vacuum. You're using gravity to just pull it out. You have to dry it. Maybe we'll use a if there's no vacuum, maybe we'll use a incubator or something like that to heat it up and dry it more quickly. But you're trying to get rid of all the water. Incubator. You want to get rid of water. Of H2O. You want the H2O go away entirely. If you have too much water, it's gonna negatively affect. There's gonna be error in your results. If you have too much water left over, you're gonna think you have more product than you're supposed to, right? And so your error is gonna be larger. Just as an example, if you rinse it out and you lose some of your filtrate in here, then you're gonna end up with smaller than what you thought you were gonna end up with. And so you know, there's something to look at for the error side of it. Now, vacuum filtration, we haven't talked a lot about. Let me just go one page over here. Vacuum filtration. Sometimes they do this. I did this in college. I did not do this in high school. There's this funnel like this. Oh, am I doing this right? Let me double check the picture on this. I can't even remember what it is. It's called a Buchner funnel. Okay. And so it actually doesn't taper off that, but here we go. Down this way. And then right here, this is actually, let me change the color on this. Let's make this, oh no, we're green. I like it. Let's make it purple. So right here is a stopper. And okay, and then you have off of here, oops, off of here, there's a little hose that comes off of here. Make it red, because all of our hoses are red. And there is a vacuum here. And it is pulling air. Okay, and right up here, we're gonna make this orange. Right here is the filter paper. Okay, and your filtrate, let's say it's on here, and it's pulling there's a bunch of holes there, and it's pulling them down, and so it's pulling the water out, okay? And so this basically, having a vacuum filtration will speed up the filtration. Okay, so it pulls more water. Definitely doesn't take as long. Oh my goodness. Doing just regular filter paper takes a long time. You put that vacuum filtration on and just like that, it starts sucking it out, and it is fantastic, obviously. Which, you know, that'd be great if we did that more often. We just don't. So anyways, this, oh, and I forgot to write out what it is. This is called a Buchner funnel. Okay, so it's just another way of doing it to get that out. So gravimetric analysis, you can do it that way. Now I'm going to expand on this for just a second longer. Bear with me. You can also do this, if you guys remember, what do we call, my dog's barking, sorry, I'm distracted. Hopefully she stops. Okay, oh, so sort of a, well, it's technically, I guess it's not really gravimetric analysis, but it kind of ties into the empirical formula stuff. We had the Epsom salt lab. And we were trying to find the number of water molecules bound to a salt. And we used heat to drive off water. So it's a little bit different in this situation because you're trying to find out, you know, you had the mass of the salt before, and then you heated it up, you drove off all the water, and then you have the mass of the anhydrated. So you have mass of hydrated salt, and then you have the mass of anhydrated, so it removed the water, anhydrated salt. Okay, and if you know what the formula is, then you can get the number of moles of each. You can find out, you subtract to get water. So you subtract to get the mass of the water, the H2O, and then grams to mole conversion. You can convert water to moles, the anhydrated to moles, and you can divide it. You can divide one by the other, and so the water is usually, there's usually lots of water molecules to one salt, and so you end up with moles of water over moles of anhydrated salt, and that gives you your ratio. So it's one more form of doing the gravimetric analysis. So at least I don't know if it technically is considered gravimetric analysis, but it's somewhat similar, so I thought I should mention it here. So hopefully that answers your question, Arya, and anyone else who had that question. So the next question I had, Arya, actually, was go over how to draw a galvanic cell with salt bridge. And I can show you that. So let's go over here. And I thought I did one recently. I don't know if I did. Oh, you know what I did? Efrain, I think I did it in the beginning of that. I think that I did it at the beginning of the, whatchamacallit, the last review session. Let's see. Hold on. No. Oh yeah, this is it. Oh, good. Let me see. Okay. I think this is it. I think this is what I started with last time. And I would be wrong. Well, what the heck? I could have sworn I did it. Did I not? Well, if I didn't, then this was a big waste of time. And my apologies. I didn't. Okay, never mind. Let me go back to what we're doing here. Really? Oh, this is the one we did last time. There we go. Okay, this was last time. Sorry, it was the one I was in before was 2. Okay, so this is a galvanic cell. And in a situation, we have zinc and we have copper. Okay, and what I did is I wrote the 2 equations. I kind of feel bad. I feel like this is not, well, let's just go over this instead of me having to draw the whole thing again, because that way it just takes a long time. So you have the two beakers, okay? And basically it's the same setup all the time. You have an electrode on the right, you have an electrode on the left. They're connected with a wire. You can put a V or some sort of voltmeter in the center. There is a salt bridge right here. Okay, and in this particular example, I picked zinc and copper because that seems to come up quite frequently. So zinc, if I give you a reaction right here, and you can see the zinc 2 plus 2 electrons gives you zinc solid, and the copper 2 plus 2 electrons gives you copper solid. And this is in a table they might give you. These are the reduction potentials. So the reduction potential was a negative 0.76 for the zinc and a positive 0.34 for the copper. And so if you remember me saying that you pick whichever one's higher, whichever one is higher becomes your actual reduction. Higher E naught for reduction gets reduced. I mean, that's pretty straightforward, okay? And in this situation, the copper has the higher E naught for the reduction, so it is the one getting reduced. Copper is the one getting reduced. Reduction and cathode both start with consonants, so reduction happens at the cathode. That means this is the cathode, copper's at the cathode. If it's reducing, you can see that it's becoming solid, which means we have copper sulfate. If you have two solutions here, usually the electrode is in a solution of its own ion. So this right here is going to be like a copper nitrate. Copper, oops, that's not a copper 2 nitrate. Oh my goodness, eraser please. Let's make it orange. It just will get confusing if I don't. So this is a copper nitrate solution. Let's just pretend for a second, okay? And then on this side, the zinc is in a zinc nitrate solution, okay? Because there have to be coppers available to add to the copper electrode, and then zincs come off into zinc solution. And so that's why they make this a zinc. Now, it doesn't technically have to be if the zincs are not going to be added to the electrode, but anyway, they are. I mean, that is the solution. Usually, what happens? Your salt bridge has to be ions that are not going to form precipitates with something. So I am saying zinc sulfate. I don't know this for a fact, but I'm pretty sure sulfate doesn't react with zinc 2 plus. So I picked zinc sulfate to be there, and so the sulfates come down. And what's happening is you have to keep a balance of the charges here. So the negatives have to go into the anions have to go into the anode side. Anode, oxidation, both start with vowels. So oxidation is happening there. Oxidation is loss of electrons. So electrons are being shot up out of the zinc electrode and across. Show them coming up right here. They're coming up out of the anode, out of the zinc anode, going across to the cathode, where they're being used to bond coppers to the copper electrode. And then sodiums, the cations have to drop down. They're not 2 pluses. Did I put sodium 2 plus? That is horrific. Oh my goodness. I'm embarrassed. Na plus. Na pluses drop down into the solution to replace the copper 2 pluses that are being added on there, because it has to keep its balance, because you got to be able to keep the circuit moving. Okay, you got to be able to keep that current flowing. Okay, if the salt bridge wasn't there, it stops flowing. So anyways, because this is oxidation over here, you're going to reverse this zinc reaction. So now it's in its oxidation form with zinc solid going to zinc 2 plus 2 electrons. And you flip the sign on the 0.76 and you get positive 0.76. So 0.34 plus positive 0.76, you get 1.10 volts. So that's basically how you set up a galvanic cell. Now from there, you can start doing your calculations of delta G equals NFE. And did I show that on the next page? Nope, that was where we got into mole fractions. So delta G, if you're doing that, that's how they're related, equals negative NFE. So where E naught is the amount you get right here, and the N is the number of moles of electrons. So you can see you've got 2 moles here and 2 moles here, so that's going to be 2. The F is Faraday's constant, which is like 96,500 coulombs. And so you multiply them all together. In this situation, galvanic cells are pretty spontaneous, which means they just happen. You just put it together and it just starts going. The E naught is positive, but the delta G becomes negative because there's a negative in front of the N, which is great because delta G, once it's negative, that means that the reaction is spontaneous. That works out very well, describing what's happening. Delta G equals negative RT natural log of K. And when you have a situation like that, actually, let me go to the next page because you have to be able to write the equation for this. So I'm just going to piggyback on this for a second. And let's go ahead and make it, we had black before. So what are our 2 equations? Okay. So you have copper 2 plus 2 electrons yields copper solid. And we had zinc solid giving us zinc 2 plus 2 electrons, okay? So the net ionic equation, the electrons are going to cancel out, leaving us with the equation copper 2 plus zinc solid gives us zinc 2 plus copper solid. And if you're talking about K is equal to concentration of products over concentration of reactants. Bracket here. The zinc solid and the copper solid don't count because they're both solids. So you end up with a concentration of zinc 2 plus over the concentration of copper 2 plus. So, and that can tell you the zinc 2 plus builds up and the copper 2 plus reaction decreases. And as time goes on, right? So K looks like it's getting bigger because it's going further and further towards its completion. I would also say this, so then you can see how you might change the reaction. If you add some zinc 2 plus, if you increase the concentration of zinc 2 plus, you're going to slow down the reaction. The current will flow. It's going to resist the reaction because you added a lot of products, so it's resisting. Think of Le Chatelier's. You don't want to say it goes the other direction. You don't want to say that it shifts back to the left. You want to say that it actually resists. It slows the reaction down because you increase the concentration of the product. If you remove zinc 2 plus, as if you were to precipitate it out, that's going to speed up the reaction, and so you're going to get more current flowing. If you add copper 2 plus to the solution, that's also going to speed it up, and you're going to get more flowing. If you remove copper 2 plus from the solution, that's going to slow it down. So hopefully that makes some sense there. Hopefully that was thorough enough on the galvanic cell. All right, yeah. But I would be happy if you have more questions about that, please post them. Okay, so that one's done. And I think I'm gonna have to go back to the other book, which is fine. So Ephraim, you had a question in regards to, let me see if I get this, where did I go? Go too far? Wait, what's this? No, semester 1. I think I am not. I went the wrong way. Sorry. Final exam review. Okay, here we go. Yes, Epsom salt. Okay. Okay. Princeton review question S. How many moles of electrons are transferred when 1 mole of potassium dichromate is mixed with 3 moles of nickel? Oh, Ephraim, makes it difficult for me the way you ask questions. All right, so potassium and dichromate, which is Cr2O7. Okay, and that's a 2 minus, right? So because we have a K plus plus a Cr2O7 2 minus, right? That's that polyatomic ion. So when you do soften dropper, you end up with K2Cr2O7. And if we're talking about nickel, I would be surprised that nickel, I'm assuming you can have nickel 1 or nickel 2. And it depends upon if your question is involving oxidation reduction, like is it a half reaction? Because if you're doing that, you have Cr2O7. I don't know if it's acidic or, again, I don't think I understand. Cr2O7. So chromium, Cr2O7, you could go to a chromium. I'm kind of blanking on this. I want to say that it's a 3+. Because I don't know what you're talking about there. So I'm going to assume that it's this situation right here. And so you have to balance by half reaction method. And so you balance the elements that are not H or O first. So that means you have 2 here. So you get 2 chromiums, 2 chromiums. Then you balance the oxygens. So we have to add 7 H2Os over here. That means we add 14 H pluses right here. And then we have to balance the charge, and we have 6 plus here, and we have 14 plus here. So we have to add, is that right? 6, 14, I guess so. 8, oh, no. Sorry. You want them to be the same because the electrons are just negative. So you add 8 electrons here. Now, nickel, I don't know. Let's assume that it's a nickel 2+. I don't know what it means. Seriously, Efrain, I don't know what your question is. You're driving me bananas, buddy. I really don't understand. There's 8 electrons here. So if it's nickel 2+, and you've got 3 moles of that, that's 6 electrons. I don't know, they both go into 24. I see, I don't know what you mean. I really don't. I don't think I can. I'm trying to figure it out, and I can't figure out what your question is, buddy. I'm sorry, Efrain. I'm gonna have to say I don't know. I need to see that. I need to see your question. You ask a lot out of the Princeton review. That's not one I'm familiar with. When you show me the thing, we can talk about it. But if that's the whole question, it doesn't make sense to me. It doesn't seem to have any context. Okay, your last question. You said you were going to go over what was on the test. I said I would answer any questions. I said that I have the, you kill me, Efrain. Let's do this. Let me show you. I think it's open somewhere. There we go. Efrain, I said I would post out all the things that I think that you should know for the final exam. So, and here it is. These are all the things I've listed here. I gave you guys the link to it already. So you ask me questions on that, and I can go over it if you're struggling with one of those things. But I said it would take too long to go over all those things in a review session. So I'm not going to do that. I am going to make those videos that you guys requested. So I need to get cracking on that. If I'm going to do that tonight, I need to get as many done tonight as possible. I've only done 2 of them, and somebody just added 1 more, which is totally fine. I welcome that. I want you guys to be prepared in whatever I can do to help you. Please ask questions. So that was the purpose. I wanted you guys to ask questions. And all these things I've been talking about are totally relevant to the test. So I have been going over what's on the test. Do you guys have another question specific that you can also set context? Like you guys haven't asked me any questions about, which is totally fine. Those big idea worksheets, which is fine. Those are sort of practice exams, the other practice exams. So I feel like maybe by providing you with the solutions, that helped you guys to understand some of that stuff, which is good. But if there aren't any other more specific questions, it's 9 o'clock. I don't mind going over, but only, I mean, I want you guys to ask questions for me to address, because otherwise I'm just kind of throwing darts at things, and you guys might be when I don't need that. And plus, we're not bookmarking in the video the questions, so anybody watching later won't know what the questions are if I just start throwing stuff out there. And as I mentioned at the beginning of the video, so there's more of you here. Like, I don't know, I wouldn't mind, I don't know if another Google Hangout would help, but I feel like if I meet you guys in person somewhere, like if you guys, I don't know if you guys study at Origins, but if one of these nights, like a Sunday night before the exam, if you guys were spending a little bit of time at Origins, like just getting the last bits kind of crammed in or whatever, I don't mind stopping by and trying to help out where I can. Totally would love to do that for you guys if that's something you're planning on doing. If not, I can't, you know, I don't need to do that. I just want to help. So we have, of course, the free responses on Wednesday, and so I can ask you guys then if you guys remember, or you can email me. But I don't want to meet at school or anything, because I think that's won't be very helpful. I think people might feel obligated to stay, or plus if you're at Origins, you have stuff to eat and drink or whatever. It's much more convenient. There's couches. Hey, you don't have couches at my room. All right. So no one's typed in any other questions. So I'm going to assume that no one has any other questions at this very moment, or maybe you do, you just don't know what to type in. I'll give you guys like 20 more seconds, and then I'm going to get off and start making the other videos, getting them loaded as fast as I can to help prepare you guys. Any other questions? Well, I do want to compliment you. There were a lot of great questions that we had this evening, and so really packed out that hour. And I feel like we hit a lot of things. I was able to cover things that are on the test. And I was able to address some of the questions that I know that some of you had. So thank you for that. Otherwise, I will just, I'll be in my room tomorrow. Before school, after school, I have a game. I have a soccer game, so I can't do anything after school. We have +2 tomorrow. I know I have some students coming in for some help during Plus. You guys are welcome to come in during Plus. I have some students taking retakes and things, but I will be in there for the entire time. I might run out to use the bathroom real quick, but I'm basically going to be there the whole time. So before school, Plus and lunch, and then of course I will be there before school. I'm going to get there as early as I can on Wednesday. My goal is to get there by 6. I wouldn't recommend showing up before 6:15 though. If you show up at 6:15, you're pretty hardcore, but you know, I remember what it was like to want to get the grades and understand the material and do well. So I want to be as available as I can for you guys. All right, Aria, you're welcome. And I will just talk to you guys soon, I hope. Good night. Get some sleep. You guys, please get some sleep the next couple nights. Sleep is your best friend.